The National Electrical Code, specifically Article 501.16 of the 2005 edition, mandates specific grounding requirements for metal vessels situated in hazardous locations. This section stipulates that metal raceways, cable trays, tight mineral insulated cable, enclosures, and other equipment must establish a connection to the grounding electrode system. This connection must also extend to the grounded conductor of the circuit, located either at the service equipment or at the origin point of a separately derived system. The underlying principle is to provide a low impedance path for fault currents, ensuring the rapid operation of overcurrent protective devices, and consequently, minimizing the risk of electrical shock and fire hazards within these sensitive environments. The requirement for multiple grounding connections is intrinsically linked to minimizing impedance to ground. Single grounding connections, while fulfilling the basic requirement, may exhibit higher impedance due to factors such as conductor length, connection resistance, and inductive reactance. Multiple grounding connections, strategically placed, effectively reduce the overall impedance to ground, thereby enhancing the effectiveness of the grounding system. In hazardous locations, where flammable gases, vapors, or dust may be present, the consequences of an electrical fault can be catastrophic. A high-impedance ground fault can generate sufficient heat to ignite these substances, leading to explosions or fires. The presence of multiple grounding paths significantly lowers the likelihood of such ignition by providing a more reliable and rapid path for fault current to flow, thereby reducing the potential for dangerous arcing or sparking. Furthermore, static discharge and lightning protection considerations have a substantial impact on the design and implementation of grounding systems for metal vessels in hazardous locations. Static electricity, generated by the movement of fluids or materials within the vessel or by external sources, can accumulate on the vessel's surface. If the vessel is not adequately grounded, the static charge can reach a level where a sudden discharge occurs, potentially igniting flammable substances. Multiple grounding connections provide a means for safely dissipating static charges, preventing the buildup of hazardous potentials. Lightning strikes pose an even greater threat. A direct lightning strike to a metal vessel can introduce massive amounts of energy into the system, potentially causing severe damage and ignition of flammable materials. While no grounding system can completely eliminate the risk of lightning damage, multiple grounding connections can help to distribute the lightning current and minimize the voltage gradients within the vessel, thereby reducing the risk of ignition. Industry standards and recommended practices such as those published by the Institute of Electrical and Electronics Engineers in the Green Book, Factory Mutual Recommendations, and Process Industry Practices advocate for the use of multiple grounding connections for metal vessels in hazardous locations. These recommendations are based on extensive research, field experience, and a thorough understanding of the hazards associated with electrical equipment in these environments. Firstly, the Institute of Electrical and Electronics Engineers Green Book provides comprehensive guidance on the design and implementation of electrical power systems for industrial and commercial applications. It emphasizes the importance of grounding for personnel safety, equipment protection, and system reliability. With respect to hazardous locations, the Green Book recommends the use of multiple grounding connections to minimize ground impedance and to provide redundant grounding paths in case of a failure in one connection. Secondly, factory mutual recommendations, which are widely recognized in the insurance industry, provide specific guidance on loss prevention measures for a variety of industrial processes. These recommendations emphasize the importance of grounding for preventing fires and explosions in hazardous locations. They typically require multiple grounding connections for metal vessels and equipment to minimize the risk of static discharge and ground faults. Thirdly, process industry practices, which are developed by a consortium of leading process industry companies, provide standardized engineering and construction practices for a variety of process industry facilities. These practices typically include detailed requirements for grounding and bonding in hazardous locations, including the use of multiple grounding connections for metal vessels and equipment. Adherence to these recommendations and practices, in conjunction with the requirements of the National Electrical Code, ensures a robust and reliable grounding system that minimizes the risk of electrical hazards in hazardous locations. The selection of appropriate grounding conductors and connection methods is also crucial. Grounding conductors must be sized adequately to carry the maximum fault current that may be imposed on them. Connection methods must be reliable and corrosion resistant to ensure a long-lasting and effective ground. The National Electrical Code provides detailed requirements for the sizing of grounding conductors in Table 250.122, taking into account the rating of the overcurrent protective device protecting the circuit. Common grounding conductor materials include copper and aluminum, with copper generally preferred due to its lower resistance and higher corrosion resistance. Grounding connections can be made using a variety of methods, including bolted connections, welded connections, and compression connectors. Bolted connections must be properly torqued and protected against corrosion. Welded connections provide a permanent and lower resistance connection. Compression connectors provide a reliable and gas-tight connection when properly installed. Regular inspection and testing of grounding systems is essential to ensure their continued effectiveness. Grounding connections should be visually inspected for corrosion, looseness, and damage. Ground impedance should be measured periodically to verify that it is within acceptable limits. Ground fault circuit interrupters should be tested regularly to ensure that they are functioning properly. Any deficiencies found during inspection or testing should be promptly corrected. In summary, the National Electrical Code requires multiple grounding connections for metal vessels in hazardous locations to minimize ground impedance and to provide redundant grounding paths. Static discharge and lightning protection considerations further reinforce the need for multiple grounding connections. Industry standards and recommended practices provide additional guidance on the design, implementation, and maintenance of grounding systems for hazardous locations. Adherence to these requirements and recommendations ensures a safe and reliable electrical system that minimizes the risk of electrical hazards. The specific methods and materials used for grounding should be carefully selected based on the specific conditions of the hazardous location, including the type of flammable substance present, the frequency of lightning strikes, and the potential for static discharge. Proper installation and maintenance are essential to ensure the long-term effectiveness of the grounding system. The grounding electrode system itself must also be properly designed and installed. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metallic water pipes, that are interconnected to form a low-resistance path to earth. The National Electrical Code specifies the requirements for the installation of grounding electrodes in Article 250.52. The resistance of the grounding electrode system should be measured periodically to ensure that it is within acceptable limits. If the resistance is too high, additional grounding electrodes may be required. Furthermore, bonding is another critical aspect of electrical safety in hazardous locations. Bonding refers to the practice of connecting all metal parts of a system together to create an electrically continuous path. This includes metal raceways, enclosures, equipment, and structural steel. Bonding helps to equalize the potential between different metal parts, thereby reducing the risk of electrical shock and minimizing the potential for sparking. The National Electrical Code provides detailed requirements for bonding in Article 250.90 through 250.102. Bonding conductors must be sized adequately to carry the maximum fault current that may be imposed on them. Bonding connections must be reliable and corrosion resistant. In hazardous locations, special attention must be paid to the bonding of intrinsically safe circuits. Intrinsically safe circuits are designed to limit the amount of energy available to ignite flammable substances. The bonding of intrinsically safe circuits is essential to prevent the buildup of stray currents that could compromise the safety of the system. The National Electrical Code provides specific requirements for the bonding of intrinsically safe circuits in Article 504.60. Moreover, surge protection devices may also be required in hazardous locations to protect sensitive electronic equipment from voltage surges caused by lightning strikes or other transient events. Surge protection devices should be installed at the service entrance and at any other point where sensitive equipment is connected to the power system. Surge protection devices must be properly grounded to be effective. In addition to the technical requirements for grounding and bonding, it is also important to provide adequate training to personnel who work in hazardous locations. Personnel should be trained on the hazards associated with electrical equipment in these environments and on the proper procedures for working safely around electrical equipment. Training should also include instruction on the importance of grounding and bonding and on the proper methods for inspecting and testing grounding systems. Regular safety audits should be conducted to ensure that all electrical equipment is properly grounded and bonded, and that all personnel are following safe work practices. In conclusion, the grounding of metal vessels in hazardous locations is a critical aspect of electrical safety. Multiple grounding connections are required by the National Electrical Code and recommended by industry standards and practices. Static discharge and lightning protection considerations further reinforce the need for robust grounding systems. Proper design, installation, and maintenance are essential to ensure the long-term effectiveness of grounding systems in hazardous locations. Furthermore, bonding, surge protection, and personnel training are also important components of a comprehensive electrical safety program. By adhering to these requirements and recommendations, the risk of electrical hazards in hazardous locations can be significantly reduced, protecting personnel, equipment, and the environment. One must also consider the specific type of hazardous location when designing the grounding system. The National Electrical Code classifies hazardous locations into different classes, divisions, and zones based on the type of flammable substance present and the likelihood of its presence. Each classification has specific requirements for electrical equipment, including grounding. For example, Class 1 locations are those where flammable gases or vapors are present. Class 2 locations are those where combustible dusts are present. Class 3 locations are those where ignitable fibers or flames are present. Within each class, there are divisions or zones that further define the degree of hazard. Division 1 or Zone 0 locations are those where the flammable substance is normally present. Division 2 or Zone 1 locations are those where the flammable substance is likely to be present under abnormal conditions. Zone 2 locations are those where the flammable substance is not normally present but may be present for a short period of time. The requirements for grounding electrical equipment in each class, division, and zone are specified in the National Electrical Code. It is essential to consult the National Electrical Code and to understand the specific requirements for the hazardous location in question before designing or installing any electrical equipment. In addition to the National Electrical Code, local codes and regulations may also apply. It is important to check with the local authorities to determine if there are any additional requirements for grounding electrical equipment in hazardous locations. Failure to comply with all applicable codes and regulations can result in fines, penalties, and even legal action. Therefore, it is essential to ensure that all electrical work in hazardous locations is performed by qualified and experienced electricians who are familiar with the applicable codes and regulations. Also, documentation of the grounding system is essential. Accurate records should be kept of all grounding connections, conductor sizes, and test results. These records should be readily available for inspection and maintenance purposes. A grounding plan should be developed that shows the location of all grounding electrodes, grounding conductors, and bonding connections. The grounding plan should be updated whenever changes are made to the electrical system. Furthermore, consider the impact of corrosion on the grounding system. Corrosion can significantly reduce the effectiveness of grounding connections and conductors. In corrosive environments, special precautions must be taken to protect the grounding system from corrosion. This may include the use of corrosion-resistant materials, such as stainless steel or copper-clad steel, and the application of protective coatings. Regular inspection and maintenance are essential to identify and address any corrosion problems before they become serious. The goal is to minimize the risk of electrical shock, fire, and explosion in hazardous locations. By following the requirements of the National Electrical Code, industry standards, and local codes and regulations, and by implementing a comprehensive grounding and bonding program, the safety of personnel, equipment, and the environment can be significantly improved.